All right, folks.
Robert has one. He also has like the cloth and like the particular thing you put.
Right, so you don't know.
So that he sounds very nice.
Oh, the pop filter?
Even though
I do. I'll get you some here in a second, yeah. All right, folks, here we go. Looking at this. I know we're like starting way late, but we're going to get into things anyway today because...
Speed running.
Every animal's instinct. Plus, already made the notes for you, basically, so we're just going to kind of read through some of this stuff. So, our next unit, we are actually starting into a new chapter here, chapter 4. We're talking about applications of the derivative. All right, how we're going to use the derivative, what's some of the power behind it here. So first, we're going to define what it means, what extrema or extrema means. Okay, so extrema is the plural, extremum, that's singular. Okay, and then extrema is plural. That comes like right out of the Latin. Okay, so definition of extrema or extrema. Let f, function f, be defined on an interval L containing C. Or is it supposed to be an I think actually. It's supposed to be an interval I containing C. Okay, we call f of C. So notice f of C, that is a y value. Okay, f of C is a y value. Is the minimum of f if f of C is less than or equal to f of x for all x values. So if f of C is like the smallest y value of all the y values that are on this interval I, okay, then we call f of C, that y value is the minimum value, okay. F of C is the maximum of f, maximum value here, if f of C is greater than or equal to f of x for all x. So it's like, okay, duh. The lowest point we call the minimum, the highest point we call that the maximum value. Okay, the minimum and maximum values, or the minimum and maximum of a function on an interval are the extreme values or extrema. Extreme because they go from one end of the function, the lowest, to the highest end of the function, the extremes of the function. Okay, so they're called the extrema, or the extreme values. The overall minimum and maximum of a function are called the absolute minimum and absolute maximum. So there are going to be other minimums and maximums that aren't the highest point, but they're like the highest point for like a neighborhood of points. But the absolutely highest point is called the absolute maximum, and the absolutely lowest point is called the absolute minimum. Okay, so example 1 here says, consider the following variations of the function f of x equals x squared plus 1. So here's f of x equal to x squared plus 1 on the interval from -1 to 2. So yes, there should be like a filled in dot there. I know it doesn't like looked at because of the copying and stuff. But that should be a filled in dot there because we are including -1. Sorry, I should probably move it up so you can see that part. Okay. All right, so when we look at this, okay, what will we say is the location of the absolute maximum? At what x value does the absolute maximum occur? Okay, the absolute maximum occurs at x equals 2, okay, of f. For the notes, let's write it out like I do, and then I'll show you like more like, you know, succinct maybe ways to put it right now. Okay, but for the note, since it wasn't specific. All right, so that's one way. I could ask you, where does the absolute maximum of f occur, and you give me the x coordinate, or you could also give me like the x and y coordinate together. If I ask you for the absolute maximum value, okay, is always the matching y coordinate. So it would be 5. The absolute, I guess I can put the word absolute there. The absolute maximum value is 5. Okay? If you want to be safe and you like, maybe you're on the test or something like that, and you're like, shoot, maximum value. Does that mean the x or the y coordinate? If you just say the absolute maximum occurs at 2, 5, you've covered your bases, because it covers both the location and the value. So you've answered the question, and that's sufficient. All right. So questions on absolute maximum there. the absolute maximum occurs at x equals 2, but the absolute maximum value is 5. Remember, value, we're talking about the y. Okay. All right. So let's talk about minimums here. So the absolute minimum of f. Where does that occur? Emma. At 0. Very good. And how'd you know? It's the lowest point. Yeah, that's it. Yeah, it's nothing harder than that. That's right. Okay, it's just the lowest point. So occurs at x equals 0. And then Emma, what is the absolute minimum value? Okay, so when I say value, I'm talking about, so let's go up to here. Absolute maximum value of f occurred here at the location of the absolute maximum, so the y value, 5. So what's the y value at the lowest point? 2, that's 2 right there. Is that the lowest point on our graph? This y value of 2? Yeah, 1. 1 is the lowest point here. Yeah, we got to be careful. Sometimes the minimums do not occur at the end points. We want to find the absolutely lowest point. In this case, it is just 1.
Wait, so how is this really any different from finding the range?
The domain and range? I mean, it's kind of like that, I guess. Yeah. Yeah.
I mean, I'm guessing you gotta get a lot.
Oh, sorry. Let's get it down. Sorry.
Straight on the range.
I mean, it's not. It's basically that idea. Yeah, it's basically that idea. Yeah. It's basically that idea. All right. So, I mean, it's similar, I should say, I guess. So the absolute maximum. All right. So let's look at this next one. This next one is still x squared plus 1, but now we're not including the endpoints. These endpoints are open circles. They're open circles, right? You can see that. Hopefully, that it looks like it should have copied well enough there, or good enough there. So absolute maximum of f occurs where? Yeah, right. We have some problems here. We can't get to 2, and so we're approaching 2.
At the limit.
We can't. Nope. We're not going to use limits. When we talk about an absolute maximum, we need a exact point. So in this case, we say it does not exist. We're going to say it does not exist. Because any value you would pick, Brandon, I could pick one I could pick one higher.
Well, wait, isn't there a thing?
Like you could say 1.99, I would say 1.999. You could say 1.99999.
A fraction that represents 1.99 repeating infinite interaction.
So
We should just write this.
we could, yes. Let me see here.
You know what that means? Yeah.
Then it would be an exact thing.
Right, 1.9 repeating.
You know what that
Right.
means?
No, I know what you're saying. Yes, yeah.
But
wait, so that's a bar over it?
Yeah. That's a really good question.
I'll have to think about that. Yes, but we say here the maximum value. There is no maximum value. There is no maximum value. Because yeah.
Seinfeld would have been like, absolutely not. You have a contention for even thinking that you can question the.
No, I have to look.
Logic of
I'd have to
math.
look. I'd have to look. Because that is a good point, but I don't know. So no, you could write it as a fraction. It would be like, I can't think of what it would be right now off the top of my head, but it would be like 1990. No, I forget what it would be.
Condescending way. It made me feel really stupid for
That's not good work.
Yeah, I don't know, but anyway. Oh, it would be. I know what it would be. It would be 19. No. Anyway, I can't think of it now. Anywho, so we say it does not exist, and so therefore, if the absolute maximum doesn't exist, that means there's no absolute maximum value either. Okay, there's no absolute maximum value either. So instead, we can look here though. Do we have an absolute minimum in this case? Let's look at that.
Oh.
Okay, so the absolute minimum of f is going to be what then, Drew? Okay, it occurs at x equals 0. And then what is the absolute minimum value, Drew? So the absolute minimum value is the y-coordinate of 0 there. Yeah, thank you. All right, cool. I'll take that too. Thank you. Okay. So yeah, absolute minimum value of f is 1. Sorry, it looks like a perpendicular kind of there, but it's supposed to be a number 1. Okay, or y equals 1, that's fine. Yep, y equals 1 is perfect. Or you could say f of 0 equals 1, that's fine too. Okay. All right, and then this last one, which is like piecewise. Okay, got some fun things going on here. Okay. Is this first one, is that one continuous? I hear no and I hear yes. So the first one is continuous. There are no jumps, holes, or gaps.
Oh, the first graph.
First graph, sorry, first graph. The second graph here, is this one continuous? Yes, even though we have holes, they're at our endpoints, and so the function itself, you can trace that with your pen and not have to pick it up or anything like that. Number 3, is it continuous? No, it is not continuous, okay? So, just remember those things. We're going to come to that here in a second. So, bless you. Is there an absolute maximum here? Absolute maximum of f occurs at, what x value here, Jack? 2. Yep, x equals 2. So it's still the same. That doesn't change. Yes? If there's no absolute maximum point, there's no absolute maximum value either. Because you have to have a maximum, like a place for the maximum to exist to then have a maximum value. So
if that point, let's say it wasn't 2, but it said 6, and x equals 0, but then...
that would be the maximum. So here the absolute maximum of f occurs at x equals 2, and the maximum value is the same as before. The absolute I'm just going to abbreviate here. Absolute maximum value is still 5. Okay, just like before. The minimum, so the absolute minimum, what is that, Jack? What would you say here? And yeah, for whatever reason, I call this one G. Yeah, and this one, sorry, I shouldn't have put F because the function is defined as G in this one for some reason. Anyway, absolute minimum of G, does not exist. There's a hole at the bottom, at the lowest point, and so we can't really figure out what the lowest point is. Okay. All right, so notice here, okay, so in summary, right, the only time when we got both an absolute maximum and an absolute minimum value is this situation where it was continuous and on a closed interval. So continuous on a, maybe I can zoom out some. There we go. So this graph right here, the very first one, the only time we got both an absolute maximum and an absolute minimum occurred at this graph, and it was because it was continuous and on a closed interval. Okay, question, Ann? Did you have a question on something, though, or? Okay, I mean, if there's something you don't understand, feel free to ask now, too. So, okay. And then this graph right here, is it continuous? We said it was continuous, but is it on a closed interval? Yeah, it's not. What we call this an open interval, right? But it's an open interval. And then this one right here, this one wasn't even, so it's not continuous. And it's on an open interval. Okay, and what's the result? The only one that we had that had both an absolute maximum and an absolute minimum is when it was both continuous and on a closed interval. And that's what you see at the bottom, the extreme value theorem, which is not something, it's not something like the intermediate value theorem necessarily, although I guess this one's important to know too. All right, so this one, you know, just like we need to know that intermediate value theorem and like be able to apply that. I know you're like all panicking right now because like none of you can remember what the intermediate value theorem says, and that, you know, if we were to ask it for a test right now, I'd be like, but that's okay. We'll look at more of that, you know, when we get to those kind of things. But the extreme value theorem, another one you need to know, if f is continuous on a closed interval, so that's what we just showed up here. That's this guy, right? AB, that's the closed interval AB. In this case, our closed interval is -1 to 2, so A would be -1, B would be 2 in this case. Then f has both a minimum and a maximum on that interval. Okay, and we're talking about an absolute.
What if it's like...
So let me get Brandon's question, and then I'll go to you, Ryan. Yeah.
I'm pretty sure Ryan has the same question.
Okay.
Not this, but for like the second and the third graph, those descriptions of the absolute maximum and absolute minimum are not like based upon just being continuous and open interval, right? Because like it could be continuous, but have its lowest point be 1, and have an open circle at 1, and then it would be does not exist, right? You're saying like
That's not the same question.
oh well.
I'm not so wait, but I'm not sure. I guess let me get your question still though.
Continuous. When we have continuous and unclosed interval,
Yeah.
it's always going to have
An absolute maximum and an absolute minimum.
But
If you don't have those,
it can just be anything. It doesn't have to be exactly what we wrote there.
correct. So yeah, so that's what I want to say. So the only way we can guarantee that we have both an absolute maximum, well, it's not the only way, but one of the ways we can guarantee that we have an absolute minimum and absolute maximum is that f is continuous on a closed interval AB. That will then guarantee we have an absolute maximum and absolute minimum. If we don't have f continuous on a closed interval, you still could have both, or one, or none. That's just it. So, but if f is continuous on a closed interval AB, then we're guaranteed to have both an absolute minimum and an absolute maximum. All right, Ryan, was your question?
This might be kind of dumb because we might come across it, but what if the f is just like a horizontal line?
So if f is a horizontal line, it's a great question. So f is a horizontal line on. So maybe if I like use some space up here, I'll just do it like right here, real quick. So we'll say it's horizontal on a closed interval. So from here to here. Okay. So you might ask yourself, okay, what is the minimum value here? Well, we go back up to the definitions of how we define what a minimum was. F of c is the minimum of f if f of c is less than or equal to f of x for all other x. So what would the minimum value of this function be? It would be 1. So this 1 is less than or equal to all the other 1s that are here. In fact, it's equal to all these 1s. So it's still absolute minimum value. What is the absolute maximum value of this? Well, that's the value that is greater than or equal to all the other values. Well, 1 is also the absolute maximum there, too. It's both.
What about just the absolute maximum? That's not existent. Like all
For this one?
Yeah. Like,
It's, like where it's located?
Yeah.
Yeah, I understand what you're saying there. That one, yeah,
That's the same with undefined then, like.
Would you use an interval or?
I don't think you'd be asked that, like, where is the absolute maximum on a problem like this? It's just the value is 1. It's the highest value is 1. The lowest value is 1. I don't think you'd be asked a question, but that's a good question, though, details. You can say the location in a different place, yeah, but I mean, yeah, the idea is that the maximum value there is 1, the minimum value is 1. So it does still follow the extreme value theorem, it's kind of, yeah. Okay. Now let's look at another definition here, relative extrema. So now we're not talking about absolute extrema, we're talking about relative extrema. And I apologize, Emma, the fact that you're gonna hear your name a lot because of the extrema, and so because I had Emma Joswiak last year, and every time she's like, what? And then so I apologize. You're gonna hear your name a lot. All right, just like I was talking about adjacent angles and adjacent sides in my first block class, I have adjacent, and I feel bad for him too. But anyway. So, consider the graph below of f of x equals x cubed minus 3x squared. The graph of this function has a relative minimum at the point what? Well, what do you guys think would be a relative minimum here?
2, -4.
At the point 2, -4. Now, why do you think we call that a relative minimum and not an absolute minimum? Because there are lower points here, right? But it's at a kind of low point, a value, if you want to say, or something like that. Okay, bottoms out and then goes back up. That's right, okay? So relative minimum is here. This is a relative minimum. Okay? And so therefore, the relative maximum, Anna, where would that one be? 0, 0, exactly right. Same kind of idea. Anna, is that the highest point of our graph? No, the end piece here goes off to infinity. So that's not the absolute maximum, but it is a relative maximum. Thank you. So yeah, exactly. In this case, if we were talking about the function overall, so like we're not giving an interval, we're just saying this is our function, there is no absolute maximum or absolute minimum here because of the fact that it goes on forever to infinity and to negative infinity. So yeah, an absolute maximum value means it must exist. Okay, so here's again what I want you guys to think about. So think of the relative maximum occurring on a peak, and that's P-E-A-K, like the top of a mountain, or a hill, if you want to use that. You know, this is kind of like our look for. It's just like when we look for, you know, something that's not differentiable, what do we look for to determine differentiability? Pointy, right? Pointy. So the same idea here. This is kind of like not very officially mathematical, right? But we're going to use this to kind of help us out. And what about relative minimums? You can say that in like a trough, T-R-O-U-G-H, or yeah, or a valley if you want to, something like that. Yes.
So is relative, like, if we were to cut it off at 1,
Yes.
so we can see that relative maximum is there, is it basically just as much as we can see right there on the graph?
Yes, exactly. So now relative extrema, though, they only occur at those hills and the valleys. And so if we, like, for example, so you want to block off, like, this graph and just say it starts at 1 and goes to infinity or something like that, so there would be no relative maximums here. There would,
Even though, like,
yeah, not be.
if we achieve a function and we know, like, that's going to be there, we can't see it, it doesn't really count.
Right, because you're on your interval there, and so it's not in the interval, it wouldn't count. Okay? Okay, so next thing we're going to look at here, as we're going to look at number 2, it says find the value of the derivative at each of the relative extrema below. All right, so...
I knew derivatives would come.
Right, calculus is finally showing up. I know you guys are like just waiting for this moment. Okay, so let's find the derivative first. Let's take the derivative here. Derivative of sine is cosine. Okay, so f prime of x is equal to cosine of x. Now, we've taken the derivative, but that's not what we're asked to do. Finally, here, we want to find the value of the derivative at each of the relative extrema. So, where do the relative extrema occur here? And we'll just say it's from 0 to 2 pi. Okay, we'll kind of like not obviously say that it goes on forever there, but just for what we've got. What is this x value here at this relative maximum? That's right, it's pi over 2, right? So we have a relative max. In fact, let's go ahead and just write those points down. Can you guys see that? Okay, yes. We have a relative maximum, okay, at the coordinates pi over 2. What's the y-coordinate for that point? Yeah, 1. Remember? Sine of pi over 2 is 1. And what about the relative minimum for this, for f? And this is f. I gotta be really careful. I'm like mixing stuff up. Yeah, so 3 pi over 2. And what's the relative minimum value? Negative 1, right? So again, this is for f. I kind of like put these off here to the side. Okay. So now if we want to find the value of the derivative at those points... Oh, question, Anna? 1.5. Use pi symbolically. Use pi because that's the precise value. So that way you know what you got it written down correctly. Okay. All right. Let's look at. So let's evaluate these things. So go ahead, guys. Take 2 seconds and evaluate. What is f prime of pi over 2? And what is f prime of 3 pi over 2? What does that equal? Okay, so f prime of pi over 2 is what? What's cosine of pi over 2? It's 0. Weird. And what is the cosine of pi over 3? 3 pi over 2, sorry. It's 0.
Didn't see that one coming.
Okay.
Oh, is that why it's like straight lines?
I saw 0 things.
All right. All right, so we'll stop there, I think, just for the interest of time. Hopefully I can give you guys an assignment, I think. Let's see.